Welcome on the Keysight virtual booth here at OFC 2021. My name is Adrien Louchet, and today I would like to talk about fake-aware conformance testing for 100G serial interfaces. So the 100G serial interface will become the workhorse of hyperscale data centers, now deploying 400G and tomorrow 800G. The 53 gigabaud PAM4 modulation is enabling the transport of 100 gigabit per second aggregated on a single electrical or optical lane, thus enabling the reduction of cost and power per transported bit. On the downside, the higher baud rate combined with the PAM4 modulation format lead to strong signal interference and distortion, as well as higher SNR requirements. The industry tackled these challenges by using adaptive digital equalizer, for instance combining CTLE and DFE to compensate for the channel loss and reflection, combined with forward error correction code that enable links running at BR10 to the -4 to operate error-free after error correction. Unfortunately, digital equalizer and retimer generate error burst, and Reed-Solomon code, such as used in the 400G and 800G designs, are very sensitive to burst errors. So what does this mean for interoperability and conformance testing? Well, it appears that the bit error ratio, which has been the reference metric for digital links, isn't sufficient to predict the impact of burst errors on the forward error correction scheme performance and ultimately to predict Ethernet packet loss. And therefore, standards bodies such as the IEEE or the OIF-CI either request to measure the frame loss ratio or to characterize the size and probability of error bursts. For interrupt and validation tests, predicting the forward error correction margin under realistic condition requires to quantify and characterize error burst mechanism. So to address this challenge, Keysight is introducing the G800GigE. Combined with the Keysight M8040 BERT platform, it builds up the industry-first fake-aware receiver conformance test solution for 100G serial interfaces. The G800GigE supports all internet speeds, so 8 x 100 GigE, 4 by 200 GigE, and 2 x 400 GigE, as well as the 800G interface defined by the ETC MSA. It can be used as a functional BERT because it accommodates 8 pattern generators and error detector on its coax interface, and offers innovative manufacturing and R&D solution combined with Keysight sampling and real-time oscilloscope. Two types of chassis are available, either with 2 OSFP112G ports or with 1 OSFP112 and 1 coax interface. So today I would like to showcase the fake-aware receiver conformance test solution for 100G serial interfaces. And let's start with electrical interfaces. The principle is to generate and analyze 100G, 200G, 400G or 800G traffic using the G800GigE and replacing some of the lane by those of a classical BERT platform that can be calibrated according to the standards such as IEEE 802.3CK or OIF-CI 112G. The traffic can be PRBS based or FEC encoded. And for this, the G800GigE and the BERT platform must be synchronized. Finally, the performance such as the BR, frame loss ratio, or the FEC margin of the receiver and the test, which could be a pluggable like in this figure, or a silicon chip, can be monitored on the 800GigE. Error bus can also be captured and analyzed. So here is a test setup. So this is our device on the test. In this case, it's the pluggable module. You can see the 8 lanes coming out the coax interface of the G800GigE. One of the lanes here is replaced by a stress lane from the BERT that has been calibrated according to the OIF-CI or IEEE 802.3CK recommendation. So the device on the test is actually the electrical receiver of our pluggable here. To measure the PR, the frame loss ratio, or the FEC margin, we are using an optical loopback using the optical interface here to a second pluggable and going to the first port of the G800GigE. Of course, in the case, for instance, you're testing a silicon chip, or in case you don't have a second transceiver to use for an optical loopback, you can use an electrical loopback back to this coax interface. In reality, the setup looks like this. So now let's have a look at typical results from this kind of test. But before this, let's recall that the KP4 FEC, which is used in 400G and 800G, can correct up to 15 erroneous symbols in a 544 symbol frame, which we call a code word, and the symbol is 10 bits. So the FEC margin describe how far a system, a link, operate from having an incorrectable error. So this means from having a code word with more than 15 error symbols. After this, the whole code word needs to be resent here and result in a frame loss. So now let's have a look at the statistics of a 200G lane. The first one is the one where we apply the stress signal from the bird, and the second one is the reference lane. And you can see that these two lanes have identical BR. However, if you look at the distribution of the number of error per frame, and as a result of the FEC margin, they are very different. So why do they have different FEC margin with the same BR? Well, if you look at the burst statistics, you will see that the first lane here experience a lot of bursts, and these are actually these bursts that govern the FEC performance and ultimately the frame loss ratio of your system. So I hope you enjoyed this short demo. If you have any questions, do not hesitate to contact your Keysight representative or to reach out to me. I would like to thank you for your time, and I wish you a great OFC. Bye-bye.